Okay, in this lesson we're going to be talking about inverse trigonometric functions. And we've used inverse trig functions before in the past where if you had like the sine of x is equal to 1/2 and you needed to solve that, the way we solved it was to move the sign over by doing x equals the inverse sine of 1/2. And we talked about when we did the law of sines that there was an issue there because the inverse sine of 1/2 actually has multiple values. So therefore, when we're saying inverse trigonometric functions, a function has an inverse. Remember that. A function has an inverse if and only if it is 1-to-1. It has to be a 1-to-1 function. This means that it has to pass the horizontal line test and it has to, or this means it has to pass the horizontal line test to have an inverse. First off, a sine curve. If you were to look at a sine curve is a function because it passes the vertical line test. However, we have an issue when we try to pass the horizontal line test. It is a function because it passes the vertical, but it does not have an inverse. So therefore, we've got to do something special to this sine function in order to make it have an inverse. So it says, however, if the domain is restricted to a certain interval, the sine, cosine, and tangent functions will have an inverse function. So when graphed on a restricted interval, the inverse of the sine function is the arcsine function. That's what we're going to talk about here in just a second. And arcsine means exactly the same thing as inverse sine. That's all it is. The inverse of cosine is arccosine, and the inverse of tangent is arctangent. So let's look at a Desmos graph, and you can see here, if I say the sine of what value, or the sine of pi over 2, what is that? It's equal to 1, and that's the only value. What if I say the sine of pi? It's equal to 0 right here, and that's the only value. This is a function because it passes the vertical line test. However, you can already see its inverse would not exist. It does not have an inverse function because if I say, okay, the sine of what value would be 1? Well, you have an answer here, you have an answer here, you have an answer here. You have multiple answers where the sine is equal to 1. So therefore, in order to create an inverse function, because think about it like this. If you were to program a calculator to where it says, okay, we're going to program some inverse sine function to where we're going to be able to find the inverse sine of 1, and it's going to tell us what value is equal to the inverse sine of 1. Well, looking at this graph, there's thousands upon thousands, actually millions of answers to that. There's an infinite number of answers that has a sine value that's equal to 1. And here we see just 3 of them. So what are we going to do? We're going to restrict our domain. We're going to say, okay, we're going to cut part of our graph off, and we're only going to allow our inverse sine values to equal a certain domain here. And here's how we're going to do it. This is the restricted domain for sine. If we look, and you can see there's the sine curve. If we were to only restrict it to negative pi over 2 to positive pi over 2, what actually happens, that covers every value, every y value that could possibly be seen on this graph. And you can see when I put that other part of the graph up there, if you pick any y value, every one of those y values are present from here to this value here. So what we're going to do is we're going to restrict our domain for inverse sine to only include values from negative pi over 2 to positive pi over 2. And notice now that this is invertible. It does have an inverse. So we're going to do that for each of these values. We're going to restrict their domain so they do actually have an inverse. So we're going to graph here on the first one, y equals the sine of x, but we're only going to graph it from negative pi over 2 to positive pi over 2. So you get a graph, which we just saw, that looks something similar to this. And now it is invertible. It passes the horizontal line test and it passes the vertical line test. So now if we were to invert that, if we were to graph y equals the inverse sine or the arc sine and we restrict our domain, then we're okay. So let's go ahead and put our domain here. Our domain for sine, we're going to restrict it from negative pi over 2 to positive pi over 2. Our range there would be now negative 1 up to positive 1. So therefore, what we're going to do now is we're going to flip-flop that. We're going to graph the inverse sine. So our domain of inverse sine will be from negative 1 to positive 1, and our range will be from negative pi over 2 to positive pi over 2, and the graph would look something like this. And that's it. So you can see now that we can find the inverse sine or the arc sine of any value from -1 to +1, and we're going to get a single x value now. Let's do the same for our cosine, and you notice that with our arc cosine, it's restricted to a different area. And the reason for that, go back and think about all students take calculus. In order to reach every possible answer, if we go back to our unit circle, well, for sine is positive here, but it's also positive here. We would never reach the negative values. So therefore, we had to include two different quadrants from our unit circle in order to reach all positive and negative values. So we did sine is positive here and sine is negative here. So we took values from negative pi over 2, which is -90, up to positive 90. We included the first and the fourth quadrant. Now, why can't we do the same thing for cosine? Well, there's a problem. Cosine is positive here and here. So therefore, in order to reach all positive and negative values, we're going to define cosine a little bit different. We're going to define cosine from 0 up to pi, so that we include all positive cosine values from 0 to 90, and then all negative cosine values from 90 to 180. So therefore, cosine of x, in order to restrict our domain, we're going to restrict it to 0 up to pi units, or 0 up to 180. When we look at the graph of that, this is what it looks like. And you see it looks just like our sine graph moved over 90 degrees. So we do have, again, a range of -1 to +1. We can plug any value in between -1 and +1, and this is how your calculator works. It's going to give you an answer between 0 and pi. Now, is that the only answer on the entire cosine curve that has a value at that point? No, there's going to be multiple answers, and we could find those later on by using other methods. We're going to revisit the period of that function and use that fact. Okay, so the arc cosine, since the domain of our original function is 0 over pi, the range of our inverse would be from 0 to pi. And the domain of our inverse would be from -1 to +1, because again, an inverse switches your domain and range, and here's what its graph would look like, which looks very similar to the original, but it has been inverted. So therefore, there is your inverse graph. Now let's look at tangent. And tangent is actually very similar to sine in the way that we're going to restrict it. We're restricting our domain for tangent from, now you got to be careful though, we did parentheses. And the reason we do parentheses around negative pi over 2 and pi over 2 is because it's undefined at negative pi over 2 and positive pi over 2. When we look at the graph, as we plot those points from negative pi over 2 to positive pi over 2, again, we have an asymptote line at each of those values. We get one period of our tangent function, which looks like this. And notice again, as we graph that, let me try this side again. As we graph that, we do reach every y value that we need. Our range would actually be from -infinity up to +infinity, which is the normal range for a tangent function. The domain for the inverse would be from negative to +infinity, and the range would be from negative pi over 2 to a positive pi over 2, and the graph would look something like this for the inverse of that tangent function. So what do we need to know about our inverse sine, cosine, and tangent functions? What we really need to know is where do we have to restrict these domains? So therefore, where our range is going to be restricted for our inverse functions, or what answers if I plug in the 0.3 into the inverse cosine, where's my range of answers going to be at? What kind of answers are we going to spit out? That's what we're going to need to know. So we need to know where our domain restrictions lie. Okay, evaluating inverse functions. We're going to use the unit circle to help evaluate these trig functions. Remember, however, that the domain and range are restricted on trig functions. So when I find the arc sine, sure, we could plug it straight to the calculator and find out what it is, but we need to use this as practice to remember what is the inverse sine of 1? What is the inverse sine of √3 over 2? Those exact values that we really need to know. So let's start out with number 1. It says, what is the arc sine of 1? First off, you need to know, where is my restrictions? When I find the arc sine, those range restrictions, what kind of answers will I get? And that would be answers between negative pi over 2 and positive pi over 2. If you want to think about your unit circle, that would be answers that are in quadrant 4 or an answer that is in quadrant 1 is pretty much what they're saying here. So find the inverse sine of 1 and just give the answer that is located in either quadrant 4 or quadrant 1. Since it's a positive value, that'd be a quadrant 1 answer. So simply what value in quadrant 1 gives us a sine of 1, and that would be a 90-degree angle or pi over 2. Number 2, we have the sine restrictions here. So since we're finding the inverse sine, we're looking for an answer between negative pi over 2 and positive pi over 2, which is either in quadrant 4 or quadrant 1. The inverse sine of root 3 over 2, since it is positive, we're looking for a quadrant 1 answer. So we're saying the sine of what angle is root 3 over 2, and that is a 60-degree angle or pi over 3. Number 3, same restrictions. However, remember what our domain is. The domain of arc sine is the range of sine. A sine function has a range of -1 to +1. If you remember that sine curve, it never goes higher than -1 or never goes lower than -1, never goes higher than +1. If you type that in, you're going to get an error because you cannot find the arc sine of -2. That lies outside of the domain of arc sine, which is just from -1 to +1. Number 4, the inverse cosine. Now, inverse cosine is defined from 0 to pi. So you're either going to find a quadrant 1 answer or a quadrant 2 answer. That's where 0 to pi is located on that unit circle. Since it is a negative value, cosine is positive here and it is negative here, so therefore we're going to find a quadrant 2 answer. And here's what I like to do. I like to say, okay, the cosine of what value gives me root 2 over 2, and that's going to give me a reference angle. The cosine of a 45-degree angle is root 2 over 2. However, we need that same answer in the second quadrant, since it's a negative root 2 over 2. So we ask ourselves, what value in the second quadrant has a reference angle of 45 degrees, and that's going to be a 135-degree angle, which is going to be the same thing as 3 pi over 4. Number 5, the inverse cosine of 3. Now the range of inverse cosine is going to be, again, from 0 to 2 pi, or 0 to pi, excuse me. However, the domain, we cannot find the inverse cosine of any value bigger than 1 or smaller than -1 because that's the range of my cosine. So therefore, if you were to type this in, you should get no solution there. The inverse cosine here, or the arc cosine of -1. Again, arc cosine is defined from 0 to pi, or pretty much from the first quadrant up to the second quadrant. It is positive in the first, and it is negative, like we're seeing here, it is negative in the second quadrant. So we're looking for a second quadrant angle where my cosine value is -1. Now, if you remember your unit circle, here's another way to think about this. Every xy point on my unit circle, the x values correspond with a cosine and the y values correspond with the sine values. So therefore, if you were to think about your unit circle, which looks something like this, where between 90 and 180, where's my cosine value equal to -1, or where's my x value equal to -1? That's a quadrantal angle. That's going to be equal to -1 at pi. So therefore, pi or 180 degrees is going to be your answer there. Number 7, now we're dealing with arctangent. Arctangent, again, is defined from negative pi over 2 to positive pi over 2, not including those endpoints. So therefore, where is it positive, though? Tangent is negative in the fourth quadrant, and tangent is positive in the first quadrant here. So therefore, we're looking for a first quadrant angle where my tangent is equal to root 3 over 3, and that's going to be, if you look at your chart or use your unit circle, that's going to be a 30-degree angle, or that's going to be the same thing as pi over 6. Where is my tangent equal to 1? Again, arctangent is defined from negative pi over 2 up to positive pi over 2, which is the fourth quadrant and the first quadrant on my unit circle. Since tangent is negative here, we're going to be looking for a fourth quadrant angle. But again, the way I like to do this, let's first find an angle where my tangent is equal to +1, and we can actually use that as a reference angle. So let's draw this, and where is tangent equal to 1 in the first quadrant? That's going to be a 45-degree angle. So therefore, tangent is equal to 1 at 45 degrees. So what angle down here would have the exact same reference angle, but it's in the fourth quadrant? And that's going to be, well, if this is 45 and we're looking for an angle between negative 90 and positive 90, then this down here would have to be negative 45. So it's very easy once you find that reference angle. If you're looking for an answer between negative 90 and 90, you can just take that reference angle, make it negative, and that puts it in that fourth quadrant like what we need. Finally, the inverse tangent of root 3, again, we're between negative 90 and positive 90. We're looking for an angle that has a tangent of root 3. Since it's positive, then we know that we're somewhere up here in this first quadrant. So we're simply looking for the tangent of what angle in that first quadrant is going to be root 3, and that's going to be a 60-degree angle, or pi over 3. Okay, next up we're going to be working some application problems, and I do want to skip number 10 because I believe there's an error in it, so let's move on to number 11. It says the angle of elevation from a football on a football field to the crossbar on the goalpost depends on D, the distance from the ball to the base of the goalpost. And you see the value there, you see a picture of it. Write theta as a function of D. So I know that the distance here all depends on the 10 and the theta. If I'm talking about the angle, I'm dealing with an opposite side and adjacent side, so I know that the tangent of theta is equal to opposite over adjacent, which would be 10 over D. However, since I want to write theta as a function of D, I want to get theta completely by itself. So here's how I'm going to do it. Move the tangent to the other side, and theta is equal to, kind of like y equals in our x equations. Theta is going to equal, when I move tangent over, theta will equal the inverse tangent of 10 over D. That's going to be theta as a function of distance. Now, hopefully, we've worked these problems before, but when we work them now, I hopefully will get a new perspective on what our calculator is doing. As soon as we see that inverse tangent now, our calculator is only going to give us a value between negative 90 and positive 90, or negative pi over 2 and positive pi over 2, even though there are infinite values there. But it says, using your graphing calculator, find theta when D is 75. Round to the nearest degree, or tenth of a degree. So our theta value when our D is 5 will be the inverse tangent of 10 over 75. And we can type that straight in. And the theta value, again, that it's going to give us is a value between negative 90 and positive 90. When we type that in, we get a theta value of 7.6 degrees. Number 12, it says two cables are secured, and we can see the picture there. Two cables are secured from the top of a 50-foot tall utility pole to the ground. The lengths of the cables are given as C1 and C2. Now we want to write theta, and we see theta is right here. Write theta as a function of C1 and C2. Now this is going to be a little bit tricky. Now first off, we know that the telephone pole, or the utility pole here, is 50 feet tall. So what I'm going to do is I'm going to let this angle right here, my red angle, be angle A. And I know that, let me write a little equation here. I'm dealing with if I'm looking at this triangle, let me outline it in red. If I'm looking at this triangle, I know that the 50 is my adjacent side, the C1 is my hypotenuse, adjacent side and hypotenuse. So I know that the cosine of my angle A is going to equal adjacent over hypotenuse, which would be 50 over C1. Now what I want to do is erase that. I'm going to leave my 50 because that telephone pole is still 50, but now I want to talk about a different angle. I want to talk about this angle, which I'm going to let be my angle B, and I'm going to outline this triangle right here, and we're going to do the exact same thing. I know that the cosine of my angle B is going to equal adjacent over hypotenuse, which is going to be 50 over C2. So therefore, my angle A, if I go back, my angle A will be the inverse cosine, if you move it over, of 50 over C1. And I know that my angle B is going to be the inverse cosine of 50 over C2. So how does that help us? Okay, now forget about the rest of this, and let's look at our theta. Okay, what's the relationship between A, B, and theta? Well, A is this entire angle right here. Well, if I was to take that entire angle and take away this portion of it, I'm left with this angle. So since my A value is defined as this, and my B value is defined as this, then my theta, which is the angle that I'm going to be looking for, will be my A angle minus my B angle. So my A angle was the inverse cosine of 50 over C1 minus my B angle was the inverse cosine of 50 over C2. So if we need a function theta, function that we can use to find theta, we could do this. We could do the inverse cosine of 50 over C1, which will give me my angle A. If you were to subtract off my angle B, which is this, then that would give you the angle theta. Now, using our graphing calculator, let's find theta if the cables are 120 feet long and 65. So 120, that'd be my C1, 65 is my C2. So I could just simply, in order to find theta now, I could do the inverse cosine of 50 over the 120 minus the inverse cosine of 50 over the 65. Type every bit of that in. And again, hopefully, while we're doing this again, is it's giving you a new respect, hopefully, for what we see when we see inverse cosine. The inverse cosine is going to be now defined between 0 and 180. My calculator only gives me values between 0 and 180. If I need values outside of that domain, I'm going to have to somehow manipulate those answers to find them myself because my calculator won't give me those answers. So therefore, it's going to restrict the domain. So when I find the inverse cosine of this, it's going to tell me my angle A. This will tell me my angle B. When I subtract the two, when I plug this in, I'm going to get right at 25.7 degrees.